Welcome to all. Today I would like to take you all on a journey to learn about complex number with the help of my assistant ChatGPT. ChatGPT is an artificial intelligence language model designed to help me with all my learning needs, including complex number. As many of you know, complex number can be quite challenging to understand, but with ChatGPT expertise in mathematics and problem solving, I'm confident that we'll be able to master this topic together. Well, believe or not, the concept and the knowledge of the complex number came up from the necessity to solve cubic equation and not the quadratic equation. So let's start off with the history of complex number. Basically, everything started in 1494. Luca Pacioli, an Italian mathematician, stated that any cubic equation in the form of ax cubed plus bx squared plus cx plus d equal to 0 is impossible to solve, as he summarized the problem with the cubic equation in his book, namely the Summa de Arithmetica. During the ancient time, many civilizations such as the Greeks, Babylonian, Egypt, Indus, Huangho, they all strive to find the general solution for the cubic equation, but they came up empty-handed. So 400 years later, the solution to the cubic equation began to take place. Scipione del Ferro, a mathematics professor in University of Bologna, he's managed to solve the depressed cubic equation in the form of ax cubed plus bx plus c equal to 0. When he found a solution to the depressed cubic equation, he decided to keep it as a secret for everyone. And in the 1526, in his deathbed, Del Ferro confided the formula to his student, Antonio Maria Fiore. Due to Fiore having the knowledge to solve the depressed cubic equation, Fiore challenged Niccolò Fontana Tartaglia to a mathematical contest. Pressured by the challenge, Tartaglia set up his mind in solving the depressed cubic equation by himself. He succeeded in finding the solution and in the end claimed his victory against Fiore. Later that time, an Italian polymath, Girolamo Cardano, asked Tartaglia about the solution to the cubic. At first, Tartaglia doesn't want to share the solution, but in the end, he told the formula to Cardano, who accepted to sign an oath to secrecy about the solution. After that, Cardano reconstructed the proof for the solution. He managed not only solving the depressed cubic, but also solving the full cubic equation. After a few years, Cardano published the Ars Magna, the Great Art, which is a comprehensive summary about mathematical finding and discovery of his own. And there's a chapter in the book that introduced method in solving cubic equation, also known as Cardano formula. Written in 5 years, may it last for 500 years. Although Cardano wrote this book, Cardano still acknowledged the contribution of Del Ferro, Tartaglia, and Fiore in creating this masterpiece. In chapter 37 of Ars Magna, the following problem is posed: to divide 10 into parts, the product of which is 40. We can write it down as x plus y equal to 10, x times y equal to 40. Through algebraic manipulation, we should get the quadratic equation such as x squared plus 40 equal to 10x. Substitute into the quadratic formula and we got x equal to 5 plus minus square root of negative 15. So Cardano comment that the idea of square root of negative number are as subtle as it's useless. Later in 1572, Raffaele Bombelli, an Italian mathematician, published El Algebra, which is a treatise on algebra and central figure in understanding of imaginary number. Bombelli completed the Cardano cubic solution with the square root of negative number by introducing a new notation, which is square root negative 1. Bombelli considered the equation x cubed equal to 15x plus 4, for which the Cardano formula gives x equal to cube root 2 plus square root of negative 1 to 1 plus cube root 2 minus square root of negative 1 to 1. Bombelli observed that the cubic has x equal to 4 as a solution and then proceed to explain the expression given by the Cardano formula as another expression for x equal to 4 as follow. He said that the cube root for 2 plus square root of negative 1 to 1 is equal to a plus bi, from which he decide the other one as a minus bi, and obtain after algebraic manipulation a equal to 2 and p equal to 1. Thus, s equal to a plus bi plus a minus bi is equal to 2a, which is equal to 4. Rafael Bombelli commented that at first the thing seemed to me to be based more on sophism than on truth, but I searched until I found the proof. In the 17th century, René Descartes, a French mathematician, used complex number extensively in his work on geometry, and he introduced the concept of complex plane, which is a two-dimensional graph that allows complex number to be represented graphically. And in the 18th century, Leonhard Euler, a Swiss mathematician who worked on complex analysis, which is a branch of the mathematics that focus on study of functions of complex variables. He also introduced the notation I that represent imaginary unit in the complex number, which is the square root of negative 1 is equal to I. So, what is complex number? From the history we learned just now, how do they define the complex number? It can be said that a complex number is an extension from real numbers, which can help to deal with the square root of negative numbers. A complex number z can be expressed in the form of a plus bi, where a and b are the real numbers and I is the imaginary unit, which is defined as the square root of negative 1. The real part of the complex number is a and the imaginary part of the complex number is b. If we have the solution of s equal to 5 plus minus square root of negative 15, we can break down the square root of negative 15 into square root 15 and square root negative 1, which end up we got a solution as s equal to 5 plus minus square root 15i. So complex number can be added, subtracted, multiplied, and divided in a way that is consistent with the rules of arithmetic for real numbers. They also have other interesting mathematical properties such as complex conjugate, which if we have the z is equal to a plus bi, so the complex conjugate will be a minus bi, which is by changing the sign of the imaginary part of the complex number. And from there, we also have the absolute value that give us the value of r and the angle for the complex number in the complex plane. Both of that will contribute to the polar form of the complex number with z is equal to r cos theta plus I sin theta. And then we have from the polar form, we got the Euler formula, which z is equal to r e I theta. And we got the most famous identity is Euler's identity, which e to the power of I pi plus 1 is equal to 0. So the real question here is, what are the real world applications that can be achieved through complex number discovery? Most applications of the complex number are resolved around engineering and physics. Basically, there are a lot used in the electrical engineering, quantum mechanics, control theory, and fluid dynamics. Complex numbers are used to represent the behavior of AC circuits and signal. They also used to represent the behavior of systems that are controlled by feedback and have enabled engineers to design the system that are stable, robust, and efficient, which later on led to the development of many important technologies such as radios, television, and computer. Basically, quantum mechanics is the study of subatomic particle, its movement, its properties. So complex numbers are used extensively in quantum mechanics to describe the wave-like behavior of subatomic particle. The use of the complex number has enabled physicists to make predictions and discoveries that would be impossible only using real numbers.